Okay, so today we're going to start, not finish this. We'll finish this stuff up after the break. There's no way we'll get this all done today. I looked at one nice thing about recording all your lectures is that you can go back and see how long things typically take, and it's literally never got done in one day. So, because just like how the analysis of variance stuff at the beginning was one. I said it's important, and it's the beginning of really everything. That's sort of what this is too now. So this is the next step. So let's say we have an experiment where we're going to give people. Let's say we have an experiment where we're going to give people a memory test, and we have a different retention interval. Okay. Retention intervals of 5 minutes, 1 hour, and 24 hours. Percent correctness, maybe a list of words like that. 90%, 70%, 60%. This should not be your honors thesis. This was discovered by Ebbinghaus in the 1800s, so you would not be breaking any new ground. So you collected your data on the effects of retention interval on memory. So you do analysis of variance, and you conclude, I haven't given you any standard deviations here, but you would get a significant effect of retention interval. So there's no doubt that you get a significant between group or treatment effect, or if you want to be more general, an effect of retention interval. Okay? Well, let's pretend that there's a whole bunch of, these are means, these are group means, and they're made up of a whole bunch of observations from a whole bunch of subjects. Okay? This would not surprise anybody. The longer time between study and test, the worse you do. Right? That's what that says. In memory. All right. So you got something like that. The numbers don't really matter here, if at all. The numbers don't really matter at all. What if you did something on levels of processing? You know what levels of processing? Anybody here take memory with you last year? Joey did. Rich did. Okay, so yeah, I mean that. Yeah, levels of processing, but levels of processing basically is the idea of a deep level of processing is when you worry with the meaning of a word. So I might have you rate the pleasantness of a word. Then you have to think about its meaning. A medium level might be something like looking at how many syllables the word has. And then a shallow or low level of processing would be to count the number of ascending or descending letters. So like a D is an ascender, a P is a descender, a Q is a descender. Okay? So you're just looking literally at the surface features of the word. You're not even looking at syllables. And that effect is pretty robust. Again, this is not something you should do for your honors thesis. This was discovered by Gus Craik and Bob Lockhart in 1973. You can do something with levels of processing. It's fun stuff. It's easy to work with. If you're interested in levels of processing, go back and read that. It even sometimes affects implicit memory, not just explicit memory. Something discovered by Challis and Broadbeck. So you do this. So you care about levels of processing because we know it affects memory. We know it's a big important variable. So you do the ANOVA and you conclude that LOP, levels of processing, affects memory. Okay. Yay. So now you've replicated things that have been replicated 1,000, more than 1,000, probably tens of thousands of times in papers, but also just in demonstrations in classrooms. It's probably literally hundreds of thousands of times. Okay. Now, some things make you go, And here's a question. What level of retention interval should you have done your levels of processing experiment at? I don't know, 5 minutes, 1 hour, 24 hours, 2 weeks, 10 seconds? Immediately? I don't know. For that matter, what level of levels of processing, which is I know it sounds horrible, should you have done the retention interval experiment? Should you have just had people read the words? Should you have had them rate the pleasantness? Should they have counted the number of syllables? Should they have counted the number of ascending and descending letters? Should they have counted the number of consonants, the number of vowels? I don't know. Should they have had to make up a story about the word? That's really deep processing. Like make up a sentence about the word. It's going to be deeper than rate of pleasantness, because now I have to think about the meaning and I have to make up a sentence. Well, and you can pick any, and any would be completely valid. Any of them would be completely valid. What you could do, though, is combine the two like this. So you have 3 levels of retention interval and 3 levels of processing. And then you have 9 groups. The G's just stand for groups. So you have a design now that looks like this. You've got what's called a 3x3 factorial design. Or sometimes you'll hear it called a 3x3 completely randomized design. And you've seen this stuff, I'm sure, in 2127, yes? Right? Factorial design. You spend way too much time, right? And it makes you angry, and you cry, and you break things, and you draw too many interaction graphs. Right? This is why I hate teaching that class. And this is why, luckily, I haven't taught it in 20 years. The last time I taught that class was literally 1997. It is the most boring. It's important to know it's so boring to teach. You're standing up there going, and then if you fall asleep, or actually your head nods while you're teaching. It's important to know. But it's boring. Not unlike this class. By the way, I have Olympic fever, which is why I'm wearing Team Canada sweater today. I've got the Olympic fever. The women beat the Americans last night 2-1, which was great. The best part is the Americans scored just after the final time went off, so their goal didn't count, which I just love because it's heartbreaking for them. And then we kicked the crap out of Switzerland and men did this one. When I say we, I was drinking coffee. I really had very little to do with it. So, or did I? So, questions about this. Does this design make sense? Right? You've seen designs like this before. So, now we've got a structural model. Now we're going to break it down, yo, as the kids say on the street. Kim had fire. That was pretty cool, right? X equals mu plus alpha beta plus epsilon. Those are not the alphas and the betas from the type 1 and type 2 error. I'm sorry. This is the way the world works. It's not my fault. Don't get mad at me. Get mad at statistics people from years ago who did this. I kind of like that fire intro thing when it came. It was like, it's on fire. It's kind of hot.
You went with the yo.
Yeah. You did. See? It's because I'm street. I don't know if you know this, my street name is Dave. So, DJ Jazzy Dave. So, good, right? Look, I get bored and I start playing with transitions. It's like when PowerPoint first came out. You don't remember that because you're too young. When PowerPoint first came out, people tried all kinds of transitions. Star wipes, things like that. Sounds were big in PowerPoint in the early days. Right? I remember my wife gave a presentation on French education in Canada in Algeria. Long story, but so she had a PowerPoint presentation because she went to Algeria in 2005 because that's the kind of thing she does. And it sort of just hit there. So they go to set it up, and a guy says, I fixed your presentation. And she's like, what do you mean? I added some sound. So every time anything came in, it and they were all different to it. And it's like, I'm trying to be a professional person doing this thing.
Yeah, like what
and now I look like, and I'm already wearing, like she was hijab on, and she had this traditional thing to be nice, and respectful, and then she said, I already feel a little bit, yes, now.
Yeah.
First I take these. Somewhere I've got a video. So any score equals the grand mean, see, plus the A effect. That's the effect of variable A. We have 2 independent variables. A, the B effect, the interaction. Oh, now it's getting interesting. And of course, error. Error is the fastest effect, as you saw in the way. So, when you look at that model, there's nothing really different. There's only one different term here. Because if we just think of A and B or alpha and beta as being like tau, the treatment effect, the only thing that's new here is the interaction. It's the only thing that's new. Everything else we've seen before. We've talked about error, that's within group, if you want to call it that, or individual differences. We've talked about a grand mean. We've talked about treatment effects. You said two of them. Right? Yes? Okay? So there's only one new term here. There's one new term. Questions about that? So the model shouldn't be anything that is something you should really worry about. Nothing to be afraid of. So let's delve a little further into this. So we can look at not only A and B, but how A and B act together. Above and beyond, how they act on their own. So how they act together or how they interact. Don't you hate when people call the payment system interact instead of interact? Does that bother you? Okay, it doesn't bother you. It bothers me. It bothers the hell out of me. You have interact? No, I have interact. So many things bother me and they shouldn't. It's a long list, man. It's a long list. Interaction is sort of like the whole is more than the sum of its parts. It's that kind of thing. And literally. Because the sum of the parts is A and B, and then we've got something added on to it. It's the effect of one variable changing depending upon the level of some second variable. Okay. The effect of one variable changes depending upon the level of some second variable. So we could look at, for example, income as the dependent variable, and the independent variable, here's one of them, is sex, so male or female. Men make more money than women. It's not fair, it's true. It's getting better, it's still true. Right, we know this, that there's a wage gap between the sexes, the same jobs. Right? It was great a couple of years ago when I had some sort of proto-men's rights activist in this class arguing with me. That was fun. This is a pretty well-established thing. We also know that in places like Canada and the States, white people make more money than non-white people, on average. It's not fair, it's the way it is. It's getting better. It's still not fair, but it still is. So I hope you don't now think that I think that's good. Can you make that clear? Okay. So there's being a woman, there's being a minority, and then there's being a minority woman, which is the hardest thing. And in fact, being a minority woman, it's worse for income on average, if you're a minority woman, than just the addition of the two effects, the effects of being a woman and the effects of being a visible minority. I know that's depressing. I think you all know that it's the way it is too, and it is getting better. I know the sex difference in wages in Canada 25 years ago was like 70 cents on the dollar, and now it's data I've seen around 90 in Canada now, which is better. It's still not fair or right, but it's way better than it was.
Excuse me, that's not actually true. That's all been debunked.
Oh boy, that was fun. Don't do that. I'm not saying I like you guys. Certain people, after you've interacted with them for a while, and then they're not your student anymore, you block them on Facebook. That's all I'm saying. That's what we do, you know. Yeah, I don't think I have to deal with this anymore because you're not going to be asking me any more questions, are you? Goodbye. Okay, so, see what happens. Do you understand what an interaction is then? The effect of one variable changes depending upon the level of the second variable. Yes? Okay? You've probably seen this exact definition in Cheryl's class, 2127, right? Okay. Oh, look, there's a nice picture. Note the equation. So, we have A1 and A2, and we have B1, sorry, B1 is the blue line, and B2 is the, I don't know, maroon line. Reddish line. The effect of B is small at A1 and bigger at A2. That's an interaction. That's what it looks like. Okay. Does that make sense? And again, I know you've seen these kind of things before, and many of you, I can see, are flashbacks to 2127. I can't believe it, man. It's like I'm back in the jungle doing interactions. Sort of through the Vietnam thing. Right? Questions about that? Okay, good. The difference between B1 and B2 is smaller at A2 than it is at A1 than it is at A2. I should say A1. And again, this is one of those typos I should fix, and every year I say I'm going to fix it, and I'm not going to. I just know that about myself. It's sad but true. So it's smaller at A1 than it is at A2. So it should say. Okay? Right? Again, so far, all good, right? Any questions? Don't feel bad if you have a question, even though I said you've learned this stuff, and I know you have. It might have been a while ago, it also might have been confusing. Okay, good, so you're okay, right? Okay. The effect of B changes depending upon the level of A. It's not supposed to look like that. It was all supposed to, the graph is supposed to go over here and get smaller. I guess I was working too much on things that had flames on them to worry about this. So all I'm saying, this is the same thing as this. A little more general. The effect of B changes depending upon the level of A. B2, you're going to be way bigger at A2 than it is at A1. 1 and 2, A1 and A2 are just levels of the independent variable A. B1 and B2 are just levels of the independent variable B. Okay? All right. You're good so far? Questions? So, remember our model is x equals 2 plus alpha plus beta plus alpha beta plus epsilon? You may guess I've said that before by the way it came out of my mouth. So we have the model has certain assumptions, just like it's the same assumptions you're going to have for an ANOVA model, such that the sum of the alpha i's, each I is just like 1 or 2, okay, or 3 or 4, up to whatever levels, up to I levels of A. The sum of the alphas equals 0. So if it makes it go up, if it being in group 1, A1 makes you, sorry, if you have level 1 of A, so A1, your score maybe goes up by 6, and if you have 2 levels, the score of A2 goes down by 6. Okay? That's actually the same thing, that was true with the regular straight ahead analysis variance, the sort of vanilla one-way analysis variance. The sum of the beta j's equals 0. So the B effects sum to 0. Remember, these are all variances. Remember that restriction when we're doing a variance? right? That things have to sum to 0. Remember that? We talked about that. So it's the same thing here. Remember, these are just variances. It's how much A's vary from the grand mean, how much B's vary from the grand mean. It has to sum to 0. The world must work that way. The sum of the alpha I beta j's sum to 0. So in other words, all the interaction effects sum to 0. Yep.
The I's are the levels, and then the J is its own.
No, I's are the levels of A, J's are the levels of B.
Oh.
Yeah, yeah.
Okay.
So what this means then is if we have, let's make it a very simple design, just a 2x2, the simplest possible analysis variance, multi-factor analysis variance design.
Yeah.
If the B's, if the B effect, we'll call it the B effect, makes all B1s, all B's go up by 1 for B1, then they must all go down 1 for B2. Because remember, they're just,
because they have to equal 6.
yeah, and they're just variances, how much something varies around the grand mean. So for A's, what's going to be the effect for A1? Give me a number.
8.
8? 8. Plus 8 for A1. So what's it got to be for A2? Minus 8. And now for the interaction, they have to sum to 0 as well, but there's an extra condition added on to this. And that's that they have to sum all together up to 0, but they also have to sum, rows and columns have to sum to 0. So if we go plus 1, minus 1, minus 1, plus 1. So 1 and 8 is minus 10. 1 minus 8 is minus 7. Minus 8 is minus 8. Negative 1, negative 2, 6. Negative 1, 8. That's where the variation comes from. Okay. So it's just there are restrictions that are put on there, and they have to work that way because they're variances. They're variances around the grand mean. The error is normally distributed independent with a mean of 0 and a variance of sigma squared. Again, it was the same thing with straight ahead analysis of variance. The only thing that's different is this interaction part. It's literally the only thing that's different. We just have this twice because we have 2 treatments. Okay? Errors normally independent, in other words, there's independent observations. They're normally distributed, I said that the other day, and they have a mean of 0 and a variance of sigma squared. So that's from the model. Questions about that? Okay, good. Now, you're going to do an F test. In fact, you're not going to do one F test. You're going to end up doing 3 F tests. An F for A, an F for B, and an F for A by B. Right? So, we have homogeneity of variance. That's just we always have that assumption, the homogeneity of variance assumption. All the variances are equal for every group. Random samples, that we never have random samples, so that's not a problem. We can violate the hell out of that assumption. We can't violate the assumption homogeneity of variance too crazily. The other day I said, what, 4, one variance being 4 times bigger than the other is kind of the rule of thumb cutoff. So if it's like, if one variance is like 2 or 3 times the size of the other one, it's probably okay. And remember, we can take care of this usually, or often at least, with a transformation. Random samples, it doesn't matter. It literally, it doesn't matter. It has so little effect on the outcome that you can violate that. And in fact, you might say, oh, that's, well, you might think to yourself, well, that's good because when we do our experiments, we tend to just choose people from intro psych. That's not a random sample. Right? But it doesn't really matter. There's a couple of things I think there. It shouldn't matter anyway, theoretically, right? Because everybody's cognition works roughly the same anyway, so it shouldn't matter. We all follow the same rules. That's the first thing. But secondly, it doesn't affect math. Normal cognition, that doesn't matter either. technically, it matters, but it doesn't matter. So you have a normal population distribution of the thing you're measuring, and kind of variable. Who cares? You can violate that all day long. You can violate it to the point where it's just binary, zeros and ones and zeros. I've seen it. I read a paper about that. In grad school, I don't read stats papers for fun. It was assigned. Yes, the Journal of the American Statistical Association is not go-to reading for me. Because I have joy in my life. So those are the same assumptions for F. They're always the same assumptions for F. Okay, let's do kind of a numerical example. And when I say kind of, what we're going to do here is I want you to assume those are numbers that are group means. Okay? So the mean for A1, B1 is 9, A2, B1 is 7, A1, B2 is 3, and A2, B2, which was my least favorite robot in the Star Wars movies, is 1. There are scores that make those up from individuals. We're going to ignore that. I don't know how many subjects there are per group. I don't care. We're going to ignore that for now. This is a conceptual thing to help you understand where the variance comes from. So we're not going to be doing any F tests here. Because we're not going to have any mean squared error. We can't because we don't know what the individual scores are. And that's where you get mean squared error. It's within cell or within group. We can't do that because we don't have the numbers. So we're just going to assume these are group means, okay? But remember, a lot of stuff's done with group means. When you think back to, I know you guys just did an assignment. Some of you did stuff by hand. Not all of you. But those of you who did, remember taking group means and seeing how they differ from the grand mean. We just have group means. And we can calculate the grand mean. Right? Question so far? Doesn't seem so bad so far, right? Or you're completely lost. That's the other possibility. I refuse to accept that. First thing we're going to do is we'll remember the model x equals mu plus alpha plus beta plus epsilon. So the first thing we're going to do is we're going to calculate the grand mean. Thanks, Mark. And then we're going to remove it. Then we're going to just remove it. So the grand mean is 9 and 7 and 3 and 1, so it's 20, divided by 4, which equals 5. Why did I divide by 4? By 4 observations.
Why did you divide by 4 twice?
No, all this divided by 4 is 20.
Yeah. And
So that's 20, which equals 20 divided by 4, which equals 5. What do you mean twice? Look, 9 and 7 is 16, 19, 20. That's 20 divided by 4, which equals 20 divided by 4. Yeah,
I was reading that whole
you're
different way.
reading it. You're reading it.
Gotcha.
You're reading it properly. That's
Okay,
all.
I gotcha.
Make sense now?
Gotcha.
You okay, both of you? Yeah?
Yeah.
Okay, good. And I'm glad you're asking questions like this, because if you don't ask that, and then you think you're supposed to do it twice for some reason, you just screw something up.
Yeah.
So if what I write down there doesn't make sense, tell me so I can, I'll never change it. It's not happening.
I just thought you were dividing.
Yeah, I get it. I see how you could misread that way. Remember, just 2 equal signs.
Okay.
Yeah. I could have written then which equals 5, which equals 50 divided by 10, which equals 200 divided by 40. They all equal 5.
Yeah.
Right? Yeah, it's just, right? Those other ones would have been odd to throw in there, but they'd all be true. Okay, so I'm now going to take this out. So it's going to be, I should have an effect here. Now this is an edit I will eventually make, where the grand mean will just disappear. I'll take that kind of care, because all for the special effects and for the YouTube hits, like I did. They keep raising the bar. I can't put ads on my stuff. Like, I've got tens and thousands of views, but I'm not. I'd like to make some money on this. Okay, they pay me to do my job. I just took 5 out of each cell. 9 minus 5 is 4. 7 minus 5 is 2. Okay, I'm not going to say the rest of the arithmetic. I've now taken 5 out of each cell. That's all I've done. I've just removed it. So now instead of these things, it's going to make our life a little bit easier. We wouldn't have to do it this way. It just makes things a little easier. Note how we can double check if we took the grand mean out, because now the score, the entries in the table sum to 0, right? Because I've taken out the average. If I've removed the average and the average was 5, 5 minus 5 is nothing. 4 and 2 and negative 2 and negative 4. Let's see, we win. Or at least we hit it properly. We're doing okay so far. So now what I'm going to do is we're going to see what the A effect is. What the B effect is. So the grand mean has been removed. We can now go on to the effects of A and B. Let's see if our A and B effects are non-zero. This sums to 6. 4 and 2 is 6. Negative 4 and negative 2 is 6. B1 is 6 divided by 2, which is 3, which is also 9 divided by 3. I just did that in there. See? We got 2 observations. 4 and 2 divided by, adds up to 6. Divided by 2, because we have 2 of them, it equals 3. B2 is negative 3. Oh, look, they sum to 0. By the way, that's not because I cooked the example. The only way I've cooked this is there's no fractions. The only way I cook this is because there's no fractions, because fractions are annoying. Right? Because we could have had, because we're divided by 4, the grand mean, we could have had quarters in here if it wasn't a whole number, and then we could have had halves in here, and then it's like 3/4 and 1/4. It's annoying. So I did make this up such that they were all whole numbers. So now what we're going to do is we're going to take 3 out of all the B1s, and we're going to take negative 3 out of all the B2s. Okay? We're going to remove it. We can see, by the way, that the B effect is non-zero. Right? By the way, if you wanted to get, in this case, what's called sum of squares for B, these are deviations from 0, but we remove the grand mean, deviations from the grand mean. 9 and 9. The sum of squares for B is 18. Those are square deviations from the grand mean. Well, from 0 to make the arithmetic. Pretty cool, right? Maybe you don't think it's cool. I do, and that's what matters. So now we're going to take 3 and negative 3 out of all the B's, which we just did, and now we get 1, 1, negative 1, negative 1. Still summing to 0, which is nice. All told. We want that. Why do we want that? Because we know we've taken out the grand mean. If it doesn't sum to 0 after you did this once, you made a mistake. It must still sum to 0. And then A1 and A2 sums to 2 with negative 2. I am not going to tell you that, I'm not going to write down that 2 divided by 2 is 1. I refuse to do that. The effect for A1 is 1. The effect for A2 is negative 1. I took 2 and negative 2 divided by 1. Divided by 2. Okay? So we're going to take 1 out of all the A1s, and we're going to take negative 1 out of all the A2s. That's what's going to happen next. Same as before, but for the A's. The Oakland A's. No. Which hopefully will move to Montreal and become the Expos. I can hope.
So for A's, you're going to be taking 1 and negative 1 from each one?
Yeah, and I take 1 from all the A1s, and I take negative 1 from all the A2s. You should be able to, just by looking at that, tell what's going to happen. We're going to get a bunch of zeros. Right? 1 minus 1 is 0. Negative 1 minus negative 1 is 0. This is what we're left with. Now, this should tell us something. We've taken out the grand mean, we've taken out the A effect, we've taken out the B effect. The only thing left, and we don't have any individual scores, so we can't calculate what the individual effects are. We couldn't get sum of squares for within group. We can't do that. By the way, the sum of squares for A is 2. 1 squared plus negative 1 squared. Okay? This, in fact, is what the math does to get the sum of squares for A, sum of squares for B, or, variable 1, variable 2, and the sum of squares for AB. But the chance of it ever being 0 these are stylized examples, let's call them. The chance of this happening is small. But, so there's nothing left there. There's no interaction of A and B now. There's none. So this doesn't mean there's an interaction, even though they sum to 0, they must. But 4 zeros do sum to 0. Yay. Questions? Do you see what I've done? You know what the nice thing about these is? Well, first of all, the first nice thing is they make great test questions. The second thing is that you can make up examples to practice. It's trivially easy. You just take a 2x2 table and you put 4 numbers in, and then you start breaking them down and just trade and collect them on your friends. Easy. The only thing is you won't be very good probably at cooking up examples, so you're going to end up with quarters and halves. That's annoying. So use a calculator instead of your head if you're not comfortable with fractions. That's fine. You know, you can graph it. In fact, I did this backwards because I didn't want to spoil it. I didn't want to do a spoiler alert. But as you can see, A2 is smaller than A1. And if we took the sort of midpoint of these, yeah, A2 is smaller than A1. And B1 is bigger than B2. We have an A effect and a B effect. And also, does the effect of B, so the difference between these two lines, does it change depending upon the level of A? No. If I was doing this myself, I'd graph it first. Just to, so I could, but you know, you graph it last and say, okay, can I look at this? Is this consistent with the numbers I got? Yeah, it is. And as you can see, I just did this automatically. So in fact, there's quarters and halves and stuff on the axis. I was just doing this for my own purposes, just to show you guys. If it was real data, I wouldn't do that because it's bizarre. The scale's weird. Okay? Questions?
Okay, so
Please.
the last slide.
Yes.
So our conclusion was that there was no interaction.
That's correct.
And there's effects of A and B.
That's correct.
Separately.
Yes.
Not interacting.
That's right.
Okay, so how would it look if there was an interaction? How would that chart look?
Let's say, for example, that here at A1, these might get a little closer.
Yeah.
Or further apart.
Okay.
One or the other.
How would we see that in like this chart? What like? What
Oh well, maybe we would do a different. We would do another example.
Okay.
See how it works. Yeah. One of the ways to look at it though at the beginning, again, you could graph this right away, or you could just look at this and say A2 is 20 less than A1. Yeah. And that's at B1. At B2. A2 is 12 bigger than B2. There's an interaction here. There must be. Mm-hmm. So you can look at it that way. And if it works horizontally, it also works vertically. 30 is the difference here, and 2 is the difference here. There's an interaction. So spoiler alert. Dude, spoilers. I subscribe with spoilers to the Vince Gilligan rule. You know Vince Gilligan, he's the showrunner for Breaking Bad and Better Call Saul, and he said after 2 weeks, there are no spoilers. Once something is aired, after 2 weeks, no problem. And I agree with him. So here's some spoilers. World War II, Allies win. You know? I love, you ever see the Yahoo Answers? By the way, the worst website in the history of the world, right? It has the all-time greatest worst question, which is how is Babi formed? don't know if you've ever seen that. How is Babby? Some of you have, apparently. Anyway, look that up. Babby spelled B-B-B-A-B-B-Y. How is Babby formed? But I saw a Yahoo Answers question once. Sometimes I just read it for fun to see how stupid people are. And someone said, I was just wondering if Band of Brothers and the Pacific took place in the same universe. Yeah, World War II. It's not like it's a universe. It's not a comic. Yeah, one was in the Pacific, one was in Europe. You dummy? Okay. Spoilers. War of 1812 ends up in a tie. Okay. Grand mean here, 20 plus 0 is 20, minus 10 is 10, plus 2 is 12, divided by 4 is 3. Our grand mean is 3. Right? So let us just subtract 3 from every cell. So now we're just going to remove it. This is a step you can actually probably skip. It just makes life easier if you do this, because you get the actual values for A1 and A2. Like it's going to be easier to do. That's all I'm saying. So instead of now these being deviations from 3, we're now deviations from 0. Just makes your life easier. That's all this. So 17 minus 3 minus 13 minus 1. So we're going to do the columns first instead of the rows. Last time we did the rows, mixing it up a little bit, calling it audible. The A effect is 2 for A1 and negative 2 for A2, because it's 4 divided by 2. It's 2 observations. They're just averages. And to calculate an average, you take the number of observations, the total, and divide by the number of observations. Again, everything is summing to 0 now, and it should, because we've taken out the grand mean. So that's 4, and then minus 4 is 0. Yes.
What if they didn't sum?
You made a mistake.
Okay.
Yeah, it cannot.
Okay.
It's impossible. So what that means is you made an arithmetic error. You made a mechanical error. So you can check every step of the way when you're doing this on a test or a quiz. You literally can. You can always check and go, is it still sum to 0? Is it sum to 0? Because it can't not. And if you make up your own examples to just play around with, you'll find that that's just how the universe works. Yeah. And usually it's easy to find. It's just some silly mechanical error you make. Because you guys all know how to do pluses and takeaways. You're university, so it's not like there's nothing conceptual you missed. It's like I just made a mistake. Like I divided by 4 instead of dividing by 3, I divided by 4 or something, or I took out the wrong number. It's typically something that simple. That's the kind of level. It's a mechanical error, the kind you would make on any math test or whatever for years. So we're going to take out 2 and negative 2. We get 15 minus 1, negative 15 plus 1. We've now got 14 and negative 14, which of course says that we got 7. Oh, and yes, again, notice how it's still summing to 0. So we have not made any mechanical errors. When I say we, I mean me. You guys had nothing to do with this. Stop taking credit for my work. But really annoying. I'm kidding. I like you guys. I like that you with that guy. It can happen that one person wrecks a whole impression of a whole year of a course. Yeah. You know, there's some great people in the class. I'm just saying. So for B and B, for B and B1, for B2 and B1, or B1 and B2. Oh, wait. For B, we have B1 is 7 and B2 is negative 7. Okay, it is right. It's just that it's divided by 5.
How'd you get that again?
14 divided by 2. Negative 14 divided by 2. That's all it is. That's all it is. Because they're just average effects, average elevation or compression of scores due to being in B1 condition or B2 condition. All it is. Oops. So let's take out 7 and negative 7 from, so 7 from B1, negative 7 from B2. Oh, what's left is now interaction. There's no dividing to do here because the interaction effects are for each cell. So it's, well, you could say you're dividing 8 by 1, negative 8 by 1, negative 8 by 1, 8 by 1. Now here's another place where people tend to make a conceptual error. They look at this and go, these sum to 0, that means there's no interaction. No, it means there is an interaction because they're non-zero. They must sum to 0. If they do not, you made a mistake. You can't get numbers that don't sum to 0 both horizontally, vertically, and altogether. Okay? So if you got like 3, 3, 1, 1, you did it wrong. Go back and look, you made probably a stupid error subtracting negatives. It's a very common mistake. Because you sort of forget that, negative 5 minus negative 5 is actually 0. Negative 5 minus negative 2 is negative 3. It's if I subtracted 2 is subtracting negative 2. That's often the kind of mistakes people make.
Dave?
Yep.
How did you get the 8s?
I just took out 7 and negative 7 from all the, was it the P's? Yeah.
Yeah.
Okay.
That's all it is. That's all it is.
So if we had no interaction, we would just see zeros. That's the difference.
All the zeros, just like the last example.
Okay.
Yep. So we have an interaction. They sum to 0 in every possible way. Well, not diagonally. You don't do it diagonally. It's not tic-tac-toe. It's not Hollywood Squares or Tic-Tac-Doe, which are two game shows that none of you have ever seen. But I just mentioned it for myself. I do a retro TV podcast, so sometimes I just take it to retro television. Just happens. There is no off position on the genius switch. It's an old button line, but I think it's hilarious. By the way, have you seen this new lettering show on Netflix? Oh, it's so good. You realize what a good interviewer he actually was? Like the first episode, he interviews some guy named Obama, and it's awesome. And you sort of think, I wish he was president. And then the next one, he interviewed George Clooney. And next month, it's, what's her name? The Pakistani girl who was attacked for getting an education, Malala, I forget her last name, won a Nobel Prize, and she's going to Oxford now. I don't know how he's going to be funny with her. He will. Okay. So, if it was just zeros, we have no interaction. Bree, looking at you, you got sort of a half hand up.
Yeah, okay. I don't know if I'm just seeing this in the wrong way or
That's
not
fine.
understanding it, but
Yeah.
so when do we know to calculate the sum over here or at the, is it like when we're looking
Doesn't
at
matter.
A?
Doesn't matter.
Okay.
It doesn't matter which one you do first. That's why you want to do first the first time and the other one first the second time.
So there's no logical order to it? That's what I didn't understand. Okay.
The thing is, you should do the most simple things first, so the A effect and the B effect, then you do the AB.
Okay. But you're calculating the sum for the effect you're looking at.
Yeah, that's right.
Okay.
So when you look at the model, x equals mu plus alpha plus beta plus epsilon, start with the left-hand side of the model. You do mu, then you do A, then you do B, or you do B, then you do A. It doesn't matter. Then you do AB, and you can't do E. You can actually do the whole thing this way if I put a whole bunch of numbers in here, but we'd be here till like Thursday next, which would be bad because the break's coming and you have to be sitting here and podcast. I'd run out of batteries. It spares. Wrap it up. Oh yeah, that's an intersection. When two lines cross, pretty good indication that the effect of one variable changed depending upon the level of some second variable. Now, when I ask you what an interaction is on a quiz, which I will, and those of you who know me know when I say it's going to be on a test or quiz, I don't lie. Like this, I will ask you what an interaction is, and your response is the effect of one variable changes depending upon the level of some second variable. That's the answer. It's not the lines cross. Don't give me the lines cross, or the lines aren't parallel. I don't care. That's a nice heuristic, and it's true. The heuristic is the lines aren't parallel. And it works every time, so it's probably an algorithm, not a heuristic, doesn't matter. The point is, it's the effect of one variable changes depending upon the level of some second variable. It is not the lines cross, because I get every year someone gets the lines cross. You know, it's a joke after you've written out the whole thing. And then put a lol or write a little emoji for it, because I want to make sure that you're not just going, oh yeah, also the lines cross.
I'm going to do that.
That's fine. But I will, when I give Taylor the key, I'll say, unless there's some indication the person is clearly kidding, give them 0 on the whole quiz.
So don't forget.
And also take other points off of tests. Do whatever you want. You have access to the spreadsheet. That's what I'm going to tell you. Also, hunt the people down.
Don't forget the LOL.
Just don't forget that. That's fine. Or a little happy face. The happy face would be fine.
Little winky smiley face.
Yeah. JKLOL would be fine. You know. All right. So you graph it, you see clearly there must be an interaction. So let's think about interpreting interactions. And this is where we're going to probably stop for the day, because I know this has been a little bit, this has been a lot of stuff. Also, it's almost time for the break. And who really wants to go to school when it's almost time for the break? I don't want to be here. You don't want to be here. You're sick of me. Okay. Be careful when you're interpreting main effects in the presence of interaction. So, when we have what's called an ordinal interaction, an ordinal interaction is when the order of the effects is preserved. That looks like this. So that's 1A2, B1, B2. So that's an ordinal interaction. The order of the main effects is preserved. Do you see what I mean by that? That in this case, A1 is always bigger than A2. It's just that that effect itself is smaller at B2 than it is at B1.
So
I feel sorry, go ahead.
if they were to cross, it wouldn't be low.
That'd be called a disordinal interaction.
Okay, because
The order of the effects is not preserved anymore.
Okay.
And I look at it this way. When I try to interpret this graph, when I say to you, I feel confident saying to you that A1 is bigger than A2. I don't have to qualify that with usually. Right? I don't have to qualify it in any way. So in this case, I am happy enough to say that A1 is bigger than A2. I can feel good by saying that, and it's easy to say. I don't have to say anything complicated. With a disordinal interaction, it's probably almost impossible. So if we had one look like this, so this would be disordinal. Is it the case that B2 is bigger than B1? Well, yeah, it probably is. Is it the case that A1 on average is bigger than A2? Well, yeah, it is. But do you feel comfortable saying to me that A1 is bigger than A2? Well, no, because it's not true at B1. On average, it's true. Look where sort of the balance point of those two lines is. Right, and I'll take a picture of this and put it on the podcast blog. But it's almost impossible for me to talk about a main effect in this case. Talking about main effects in the presence of interactions is exceedingly difficult. Some people do it, and some people don't. It's almost a stylistic thing. If you think it's okay and you can feel comfortable saying something, that's fine. But I just can't. In the case on the right, I can't. Some people say never talk about main effects in the presence of interaction. I think those people are overdoing it. It's safer. But the people do that all the time, and I think it's okay. It's a little more conservative, that's all. So take a look at previous data, take a look at what you would expect to happen. That's part of where you make that decision. All right? Questions? So far, not that bad, right? Okay, it gets a little more hairy next time around.
Dave, can you just show me where the
Those of you watching the YouTube video will not realize that over a week has passed, when last we met, previously on Site 3256, we were talking about interpreting interactions. And we talked about ordinal versus disordinal interactions and how difficult it is to interpret main effects in the presence of interactions, especially disordinal interactions. In fact, I would go so far as to say I wouldn't talk about main effects if I had a disordinal interaction. Remember, disordinal interaction is when the order of the main effects is not preserved. An ordinal interaction is when the order of the main effects is preserved. I basically look at it this way. If I can look at a graph and I can say A1 is always bigger than A2, I'm happy. If I have to look at it and say A1 is bigger than A2 but except at B2, then I can't talk about the effect of A anymore. Because I put a qualifier in there. In other words, I just started talking about the interaction. Okay? And I know that was, again, if you're watching the YouTube video, this was literally seconds ago. However, if you're like everybody else here, you haven't thought about this stuff in a week and a half, do you guys have any questions? Okay, so I hope it makes some sense. And like I said, it's really basically, in a lot of respects, I think of it this way. Like I said, it's common sense. If you look at it and say, am I confident in saying A1 is always bigger than A2 in the data I put out there? Then yeah, I'll talk about the effect of A. But if you can't do that without saying, except at B2, if you got to do that, you can't interpret the data effect. You just can't. It's there, it's just hard to interpret. So I'm talking about going from the step of data analysis to actually interpreting the thing. Okay? Like I said, it's probably impossible with disordered interaction. Some people say you should never talk about main effects in the presence of interactions. I think they're overstating the case, personally. But they probably think I'm understating the case, but they're wrong. Okay. Now we're fine. So, the same thing we did with sum of squares and degrees of freedom with one-way ANOVA, we're going to do with this what we call factorial ANOVA. Sometimes also called a completely randomized design. So the model, remember, is x equals mu plus alpha plus beta plus epsilon. You might gather from the speed with which I say that, I've said it a few times in my life. So what we're going to do is see if we can get, excuse me, let's think of the sums of squares. Sum of squares total equals sum of squares A plus sum of squares B plus sum of squares AB plus sum of squares for error. The only new thing in here, by the way, is the interaction. We've got a main effect, and we got two of them now. So we're not tau anymore, we got alpha and beta. And we still have error. Error's going to be calculated the same way. Right. So, here we go. Sum of squares A is the square deviations of column means. So if you think of A as in columns and B as in rows, it doesn't have to be, by the way. But I'm going to put A in columns and B in rows. These would be square deviations of column means from the grand mean. Okay. So that. Sum of squares B, well, square deviations of row means from the grand mean. What we're doing here is we're collapsing across, so if we go column means, we're just collapsing across rows. We go row means, we're collapsing across columns. We're ignoring or averaging. Remember when we did the averaging, we were breaking it things down, and you'd say, what's the effect of A? Well, we got like say 3 and negative 3, 6 and negative 6, we divide it by 2, we're collapsing across something. That's all we're doing. That's all I'm talking about here. Okay? Those are exactly the same as what we get when we do sum of squares treatment. Except we don't have rows and columns, we just have maybe just columns, I don't know, however you want to think of drawing it out. Okay? Good so far? The weird one and the new one is sum of squares for AB. These are square deviations of cell means, and the cell means are the individual groups. Okay, so if we've got, erase that. So if we've got just a simple 2 by 2, the simplest possible factorial design, we can get row means, column means, but we can also get the means of individual groups. Group 1, 2, 3, 4. We now have the square deviations of those cell means from what we would expect if there was, what we'd expect from given the row and the column means. Okay. In other words, you know, we broke down those tables again. I realize it was a while back, but if we had an interaction, we were left with like +1, -1, -1, +1, right? Those are deviations, because we've taken everything else out, and what we would expect, just given the row means and the column means. Okay. So in that case, +1, -1, -1, +1, the sum of squares for interaction, or for A and B, if you want to call it that, would be 4. 1 squared plus -1 squared plus -1 squared plus 1 squared. Okay. Questions on that? So remember, we broke it down, and we ended up getting, break it down, you know, and we got stuff left over that we then said was interaction. Okay. Sum of squares error. That's the square deviations of individual scores, which we haven't even dealt with because it's just extra arithmetic. But it's from individual scores from their cell means. So that's, you know, whatever the hell the scores were, we don't know. I thought about that. It's just so much extra arithmetic. There's no reason to do it. So we partition these sum of squares, and when you partition sums of squares, degrees of freedom go with them. So there's the sum of squares. Oh my God. It's actually not that bad. It looks and goes, well, triple summation sign at the end. Yeah, because you got a row, column, cell. You got to do it 3 times. Nobody does this. I'll show you how to do it. I've already posted a video, by the way, on my website at davebuckbeck.com. God, I feel so horrible saying that. I feel really kind of weird whenever I plug into my website. Like, there's no ads. Put ads on it. It make you bad and say you have to click on them or you don't pass the course. I think that would violate Google's terms of service. I'm pretty sure it would. But if you look there, there's already a video in there from that Irish guy telling you how to set up. Oh, it's not from the Irish guy. He doesn't have one for Factorial ANOVA. He has one how to do Factorial ANOVA with Excel, but not with SPSS. I'll also talk about one today. Why am I talking like this? Simply I'm talking like Christian Slater. Christian Slater. Some of these are really for me. So I'll show you how to do it today. It's that easy. But there is a video there I posted in the stats videos section. Okay. So this is sum of squares total. It's going to be big A minus 1. Total number of subjects in the experiment. This is going to be A minus 1 and B minus 1. The effect of A and the effect of B. Okay? It's not so bad, right? Before it was, remember, number of treatment levels minus 1. Well, we got A level. We got little a levels of variable A and little b levels of variable B. The interaction, I mean, you can see this in front of you, so it's not like I'm telling any tales at school or any spoilers here. A minus 1 times B minus 1. Now, remember when we're thinking about These things always have to sum to 0. So let's go back to a standard 2x2 design, right? Give me a number.
8.
8 is perfect. Where do you want to put it?
B2A1.
Okay, that, minus 8 plus 8 minus 8. I had 1 degree of freedom. Okay, so let's try it again. Let's make it 3 levels. So I'll pick 1, 7, and I'll put it there. Give me another number. Okay, 4, thanks. Where do you want me to put 4?
B2.
B2A1?
Sure.
Okay. Okay, wait a second. Now, what's this one have to be? A1, B3. Minus 11, because that's plus 11. Which means that has to be plus 11, plus. I had now 2 degrees of freedom. It works out that it's levels of A minus 1, levels of B minus 1, multiply those 2 things together. Okay. For each group, let's just think about each group. How many degrees of freedom do any of the groups have? Doesn't matter how many groups there are. It's little n minus 1. Right? Number of subjects in each group minus 1. How many groups are there? Not up there in my example. In general, how many groups are there? A times B. Right? Because if A is 3 and B is 2, we got 6 groups. 3 times 2 is 6. So it's AB times n minus 1. If you feel like proving the identity, that all those things add up, you can. Go nuts. I'm not doing that. Like I mentioned before, I used to love doing that when I was in high school. I loved proving identities was my favorite math thing. Because it's a puzzle. I love a good puzzle. Puzzles like that, I don't like a jigsaw puzzle. Pretty boring. I found an entropes. My brother, not my brother-in-law, Isabel's brother-in-law, loves doing puzzles. And it's like, all right, puzzles. We're at your cottage. Where are we drinking? You know, it's no time for puzzles. You're kind of drinking time now. Come on. So, what are the expected values? Now, this is where we talk about expected values in last quiz. We talk about expected values. Like tau plus epsilon and epsilon. So we're going to think of it that way. Again, it isn't precisely that. I'm sort of using a shorthand. I'm not going to use like n times sigma squared sub tau or whatever, or sub a. Okay. But if you remember, for simple ANOVA, the expected value for mean squared treatment is sigma, is epsilon plus tau. And the expected value for mean squared error is epsilon. So we must divide mean squared treatment by mean squared error to find out if we had an effect. We were isolating tau. So that's why we have to know the value of the expected value of the mean squares. Okay? Well, we have to do the same thing for mean squared A, mean squared B, mean squared AB, and of course for mean squared error. You can probably guess that A and B aren't going to change from this design, from the original design, and neither is mean squared error. The one that's interesting here to do is mean squared AB. You get what you would expect. Mean squared A is alpha plus epsilon. It may be the case that you have old versions of this that have a typo in them. It may have a sigma or something instead of an epsilon or something. I don't know. I think maybe I changed that. Mean squared B is beta plus epsilon. That's the effective level of A, the effective B plus error. Just like you'd expect. We're changing the taus to A alphas and betas. Oh, beautiful. Mean squared AB is alpha, beta plus epsilon. This is usually the point where somebody in the class goes, that's where the word alphabet comes from. And they're right. Somebody has been thinking that, but they didn't say it out loud because they thought, I think I was supposed to know that. But that's where the word alphabet comes from. And, this is great. Look, we know totally what we're going to divide by. right? We're going to divide mean squared A by mean squared error, mean squared B by mean squared error, mean squared AB by mean squared error. Do you see why we're going to divide those terms by each other? Because we're trying to isolate the effective A, the effective B, or the interaction term. Right? So that all makes complete sense, right? Yeah? You okay? You good? I know you had a break. We had a break. Again, for those of you just listening, watching the YouTube video, who aren't you guys? I don't know why. There's no cats in it. It's not a YouTube video. No, nobody's eating a Tide Pod. A Tide Pod. Who would have thought? Like, you can now make people do anything you want, right? Here's a new one. It's called the Cyanide Challenge. Eat some cyanide. See if you live. People will do it. Don't do that, kids. We divide all these things by mean squared error to get our effects. Great. The world is an easy and happy place. No, it's not. There's always a but. There's always a however. These expected values are only the case if you are interested only in those particular values of A and B. So in other words, remember we had retention, this is quite a while ago, we had retention interval of low, medium, high, and we had, 50, whatever the hell it was. Levels of processing, low, medium, high, and I think our retention intervals were 5 minutes, 1 hour, and 24 hours, I think. That's saying you're only interested in those levels and nothing in between. Oh, shit. I think I might be interested in what's in between. These are called fixed effects models. Fixed effects models. Why does it have to be like this? Because of math and how the universe works. It's not my fault. Don't shoot the messenger. What if we randomly chose our levels? Literally put all the possible levels in a hat and then drew out 3 or 4 or 2 or whatever the hell you want. If we did that, the math is going to have to take into account the fact that that extra level of randomness is in there. And that's going to probably, in fact, definitely, will change our expected values. This is called a random effects model. So if both A and B have their levels randomly chosen, the expected values work like this. Oh, that's weird. The expected value of mean squared A is alpha plus alpha beta plus epsilon, and mean squared B is beta plus alpha beta plus epsilon. The interaction is also in there. Dude. The expected value of mean squared AB is alpha beta plus epsilon. Oh, that's the same, and that's the same. Okay, so that's not so bad. It's not so bad. What we're going to do now then is to get the effective A, we have to isolate A. Okay. So we're going to divide the mean square for A by what? I know some of you have the notes in front of you, but even if you don't or do, take a look at this. What would you divide mean squared A by? It's not that funny. What would you divide mean squared A by to isolate the alpha? Yeah, please.
Mean squared AB.
Yeah. So in fact, mean squared AB becomes an error term for mean squared A and for mean squared B. It's weird. I know you were taught in 2126 and up until just last week, you always divide by mean squared error. No, you don't. Here we're going to divide the error term for these two main effects is the interaction. The error term for the interaction is still, thankfully, mean squared error. Okay? And that's simply because you randomly chose the levels of A and B. We don't do that often. We don't do that often. That's much more common in like field work. And let's say you were, I think the book uses an example of tire wear. Is that what they use, I think, for random effects? if you were randomly, if you were to look at where of different kinds of tires, and you were going to look at different cities in Canada, you couldn't test them in all, you're interested in all possible cities in Canada. You can't use all possible cities, so what you do is you randomly choose 5 of them. Okay? Then the math works. If you just pick 5, but you want to generalize to all cities, you probably should do it. What about a mixed model where A is fixed and B is random? So this would be, again, with the tire where you got, say, 3 kinds of tires, and that's 3 possible rubber compounds, or I don't know what tires. 3 different compounds of rubber, soft, medium, and hard. Formula 1, it's whatever. It's a little tiny bit of about tires from watching auto racing. And we're going to randomly choose a bunch of cities. So one's fixed, that's the tire hardness, and one's random, that's the cities. Mean squared A is, I said A is fixed, by the way. This is not a freaking typo. I know it's counterintuitive. You would think that it would go with what was with the random effects. No, it doesn't actually. It goes like that. So in this case, we're going to divide our fixed factor, mean square, by the interaction, mean square. And we're going to divide our random factor, mean square, by the error, mean square. And happily again, interaction remains the same. Good. Okay, that's not so bad. We have to know these things. I realize it's counterintuitive. It just doesn't make a lot of sense because you think, oh, well, you said the random one looks like the one at the top. Well, that's a fixed. Yeah, I know. It just is. Yeah. You got a question or?
It was trying to wrap my head around the rationale behind it. Is it basically because since beta is randomly chosen, then you don't have to worry about the interaction as much, or?
No. It's because of the math and the calculus behind it. It's basically calculus's fault.
It's because math.
It's because the universe works this way. It's really, it just is. Yeah. It's kind of like, yeah, it's just because math. Yeah, let's just go with that. Yeah, it's the.
Maybe.
If I haven't got into this, it's a long. It'll take the rest of the class. It's. Yeah, and we don't have that kind of time.
So the assumption is that AB is going to be 0.
Okay. So here's a question. We're assuming with a random effects model, or sorry, a point. We're assuming with random effects model that the levels of the random factor are randomly selected and independent of each other. So in other words, when I chose the 5 Canadian cities to test my different kinds of tires, I had all the names in a hat and I randomly chose them. And if I chose Sault Ste. Marie, it doesn't mean I don't also choose, whatever was close by, Sudbury. Right? Could happen. There's no effect of that. There's no random events. They're independent events. Now, so the question then comes, students have asked this point, what are we doing when we do our experiments? We're doing a random sort of effects, mixed effects model, kind of, sort of, not really. So the question you have to ask yourself is, did you actually randomly choose your levels? Because that's what changes the math. It's because that randomness gets in there. And we have to account for it with the math that's behind how analysis of variance works, how the expected values work. Did you randomly choose them? If you did not, just call it use a fixed effects model. It's a better approximation. Okay? So you didn't randomly choose your levels. You never randomly choose. I've never, ever in my entire career randomly chose levels for things in an experiment. It's never occurred to me. Right? Whoops. Screw with that. So did you actually randomly select your levels? If you did, and I don't, wait a second. I think one student once did. Not mine. But one of our honor students did once randomly choose levels. And I remember telling her when she was giving her thesis talk, like when she was practicing, saying you have to reanalyze your data. It's easy, just go divide by a different mean square. You have your output on you, we'll do it right now. It was really simple. And you can actually change her results, which was good. But this, and I review for journals all the time. I've never seen anybody use random effects models. Doesn't happen. Okay. It happens in other things. Like I said, the example with choosing the different cities, you would use a random effects model, and you want to do that in that case. It makes complete sense. We don't tend to do this. So the better approximation is a fixed effects model. But technically, when you will see people, wow, we do it all the time. We draw those graphs with the lines where the points are connected. That's misleading because we can't interpret the things in the middle. We do it all the time. It doesn't matter. It's not a huge deal, but it's a little weird. People mostly ignore that. Just to move my pointer here. Okay, so let's think of our analysis of variance summary table. Just looks a little bit different now. Source of variation, degrees of freedom, mean square. I don't have sum of squares written in there because I couldn't make the table fit on the slide. But these kind of things make great test questions because I can have a fill in the blank thing again. Right? And then you have to know, oh, sum of squares equals, mean square equals sum of squares divided by degrees of freedom. Degrees of freedom have to sum to the total. That's all people are moving. I don't mind from walking. That's when people stand at the other side of the classroom and just have loud conversations and laugh. It makes me want to break people's necks. I don't, because I usually yell. That's not the first one. First was try to keep it down, and then I do go from there. So that's the ANOVA summary table. Right? So we're just going to take mean square A divided by mean square error, mean square B, mean square AB minus mean square error. But remember, that's for fixed effects models only. Now, do we ever use random effects models or mixed models? It happens so rarely. I want you to know about it, and there's a reason we get to repeated measures that it makes really good sense that I've talked about this. Because you might be wondering right now, why are you telling us about something that no one ever does? There's always a reason. I plan these things. So there is a reason we're going to talk about it shortly. But unless someone has told you it's a random effects or mixed model, it's a fixed model. Unless you're explicitly told levels were randomly chosen. Okay? Like I said, I've seen it once in my whole career. Only one student did. Questions so far? Okay. You can make these things bigger. Why not add in a third one? What about C? So we got C1, C2, A1, A2, B1, B2. So we've got now, 8 groups. This is a 2 by 2 by 2. Can we talk about these things beyond like 2 levels? Oh, sorry, 2 independent variables in 2127? Yes or no? No? Don't think so, right? Now, in this case, you have 3 main effects, A, B, and C. You have 3 two-way interactions, A, B, AC, and BC, and a 3-way interaction, A, B, C. A 3-way interaction is when the 2-way interactions change depending upon the level of some third variable. A 941-way interaction is the 940-way interactions change the level at some level of the 941st variable. A 7-way interaction is the 6-way interactions change depending upon the level of some 7th variable. So all this is, by the way, this is not uncommon. You will see, you guys probably have read enough of literature now that you've seen experiments that have, let's say, Well, think of this. We could do our memory experiment. So we've got levels of processing. We've got time, retention interval, and let's go with two kinds of tests: implicit and explicit. Right? So you guys took memory with me, but implicit and explicit memory tests. We get two kinds of tests. So that's A. We've got time, short and long, 5 minutes and 1 hour. That's B. And levels of processing, low and high. That's C. That's the experiment. That's not a complicated experiment. And I can tell you that experiment would deal with three-way interaction. So you've seen these things. It looks complicated there, but when you think about it now with an example, it's not that bad. Right? Because again, time, test type, and levels of processing. Yeah, sure. What's the problem? I will say, if you do your honors thesis with me, I won't let you do this. And the reason is because it's hard to explain. It's not because you can't do it, you don't have the ability. It's not true. You go through this course, you can do it. But it's explaining it to others that's the hardest thing. It's hard explaining three-way interactions to a general audience at the thesis conference. It's hard explaining it to everybody's mom and dad that the two-way interactions change depending upon the level of the third variable. It's hard explaining it to a lot of people. They don't get it. Right? We get it. So I usually go, let's not do that. It also makes your experiment bigger, doubles the size of your experiment. You know, why do you want to test 80 people? They're intro students. I don't even like interacting with them. I shouldn't have said that out loud. I don't teach intro. That's why. No, it's because other people are better at that today. I think. So now we'll imagine this model. X equals mu plus alpha plus beta plus gamma plus alpha beta plus alpha gamma plus beta gamma plus alpha beta gamma plus epsilon. ABC, alpha beta gamma. There's no C in Greek, so they go with gamma, G, difficult. X equals mu plus alpha plus beta plus gamma plus alpha beta gamma alpha beta gamma epsilon. So that's not horribly complicated, actually. It really isn't. It's exactly what we think. Three-way effects, two-way interactions, a three-way interaction, and of course error. It's always our lonely friend at the end, sitting there going, "I'm just a mistake." I feel bad for error. But without error, we couldn't do I don't know. I thought I had a thing there. This looks like this. There's a three-way interaction. Oh, I see. See, look. Here's the two-way interactions. We got a disordered interaction over here and an ordered interaction here. Can you describe this interaction, or these interactions, without mentioning C? No, you cannot. So you have a three-way interaction. Oh, that's not so bad. I can draw you an example from the real, what it would look like with our levels of processing. Okay, so here's the explicit, with the implicit over here. Okay. Graphs. There we go. One more. Hours. 1 hour. Okay, so here we go. Explicit memory, high level of processing. You're going to have some decline. So it's high. Low level of processing, you're going to have more decline. Implicit memory. High level of processing. Right on top of it, because there shouldn't be an effect at all, will be the low level of processing. That's actually how the world works. Some of you guys, I taught you that in memory, and you know it. So it's not like it's hard to understand a three-way interaction. It's totally doable. Hey, we could throw in presentation type. Are they blocks? So they get all. Yeah, we could throw in presentation type, block for a presentation, and now we have the same subjects, which is repeated measures, right? Versus switching back and forth, and then we get flowing interaction. It's no big deal. When you think of examples, it makes things a little bit easier than just A's, B's, and C's. Okay. Questions? So there are some advantages to these designs. We can study interactions. Very many of our theories have interactions in them. The idea that levels of processing affects explicit memory, not implicit memory, is predicted by all kinds of different things, all kinds of different sort of theoretical approaches to human memory. We expect sex differences favoring males in spatial tasks and favoring females in verbal tasks. That's a three-way interaction. Dude, awesome. They're actually, once you've done it a few times, and even I hope this one, the example I gave you up here, it's actually not that hard to interpret these things. It really isn't. It's hard. It's sometimes hard explaining it to people when you haven't done that a lot. Right? But it's doable. It's doable. Now, here's a disadvantage, which should have a title, and it doesn't. I don't know why. Is it fixed, random, or mixed? Well, the thing is, typically you just say it's fixed and move on. But really, it's because it's the closest thing to what we do. Right? These things can get big. Okay, when I add, and there's only had two levels. If I had a 2 by 2 by 2, I had 8 groups. What if I had a 2 by 2 by 2 by 2? Now I get 16 groups. Right? And if I learn to speak English, so if we've got 3, we get the following effects, right? A, B, C, CA, CB, CAB. Now if I add on down D, yeah, D, DA, DB, DAB, DC, DCA, DCB, DCA. That's how many effects I have to test. That's how many is that 2, 4, 6, 8, 10, 12, 14, 16. I have 16 different ANOVAs or F-tests to do. Add in a fourth, and I have 32. Look at how big that thing is now. A, B, C, D. Let's say there's 10 subjects per group. You go from something really simple. It's like, well, this is how I'm spending the rest of my life testing these people. Probably you have to start measuring things in geological time. It's a long period of time. And explaining a four-way interaction is hard. Because you have to think. 3 dimensions is easy. Look around us. That's pretty good. It's a 3-dimensional universe. 4 is hard. 4 is hard to imagine. Questions on that?